Hi guys, lesson 10, chemical equations is next. So what I want you to think about when we're writing chemical equations is the example of vinegar and baking soda that we all are familiar with. So what we're going to do is we're going to have reactants. So that would be the vinegar and the baking soda. And we're going to have the product, so what's produced. So when you put those together, it's very exciting, especially when it's in a volcano form and it produces this wonderful gas that bubbles up and looks like lava. So what's happening is we're actually seeing a chemical change. So that's going to be accompanied by one of the following events. Because remember, a chemical change makes a new substance. So that substance could be a gas, like vinegar and baking soda bubbling up. It could be energy released in the form of heat, so an exothermic reaction. You could see a change in color, which alone won't tell you a chemical reaction has happened, but if it's a new substance, it certainly does. And you might see it go slightly cloudy. So that means that there's actually little tiny solid particles within the liquid that are reflecting the light and make it look cloudy. So what happens is equations might start with the word equation, or they could give you a skeletal equation. And what you have to do, regardless of what they start with, is you need to write it out with the proper chemical formulas. So this is why we've spent so much time learning how to write ionic compounds and use a solubility table. That's also important. First example, solid magnesium metal reacts with aqueous hydrochloric acid to produce aqueous magnesium chloride and hydrogen gas. So this one, right off the bat, we've got a whole bunch of words in there that we need to figure out. First of all, figure out where your equal sign is. And in chemistry, our equal sign is shown with a one-way arrow like this. So this is separating what we have reacting, or our reactants, from what's produced. So in this question, it's saying magnesium metal reacts with hydrochloric acid to produce. This is where our arrow needs to go. And then we're going to have the other two, magnesium chloride and hydrogen gas, on the product side. So once you've taken the words to the skeletal equation, then you can start looking in your data booklet for how you would properly name these. So first one, magnesium. It says up here solid magnesium metal. When you're just naming an element like that, you're going to look on your periodic table of elements and you're going to go to that little box on the second page that talks about the polyatomic elements. So in this box, we have hydrogen, oxygen, fluorine, chlorine. We have a number of elements that come naturally in pairs, or for phosphorus and sulfur, group of 4 or group of 8. These are the only elements on the periodic table that are going to have a subscript or a little number when they're written by themselves. That's what this chart is saying. So if you ever have something by itself, like in our question, we have magnesium by itself. If it doesn't show up in this little box on the periodic table, which magnesium doesn't, then there is going to be no subscript for magnesium. You're going to write that just as magnesium, and then they told us it was a solid. Now we're adding to that hydrochloric acid. So this can take some looking in the data booklet, but you do have lists of acids and other things in your data booklet. So if you just keep going, here's a page of acids. This is page 12. I believe. Yes. So on page 12, you have a whole list of acids. The first one, hydrochloric acid, is actually given to you right there. You'll learn how to name acids later on in grade 11, but for this one, it's HCl aqueous. So that's just a matter of finding it in the data booklet and copying it down. Now, magnesium chloride, when you see that ending IDE on chloride, you should immediately think ionic compound. How did I write the chemical formulas for ionic compounds? Well, I wrote down the charges above the words, and I crossed the charges if I needed to. So that means I need to find the charge for magnesium and the charge for chlorine. So back to my periodic table. The charge for chlorine looks like it's -1, and magnesium is +2. So I'm going to write above these their charges. And since they don't balance right now, 2 and 1 are not balanced, I'm going to cross the charges. The 2 goes after chlorine, the secret 1 after magnesium, and it will look like that. Now, it did tell us up in the question that this is going to be aqueous, so we don't need to look on our solubility table because they've already told us that. Last thing we're creating in our product side is hydrogen gas. Now, if you go back to your periodic table, hydrogen is one of those elements that shows up in this tiny polyatomic element box. So when you look at hydrogen there, if you have hydrogen by itself, which we do, hydrogen gas, they always come in groups of 2. So you're not going to just write an H. You'll have to write H2 gas. So this is the first step. You've got to get your equation written with proper chemical formula and states for every single element. And then we're going to do something called balancing. So what balancing is balancing is making sure that we obey the law of conservation of mass. So that was something we looked at in the previous lesson. What the law of conservation of mass says is if I start with, let's say, 10 hydrogen atoms, then I can't just mysteriously lose hydrogen atoms. Once a chemical reaction happens, the hydrogen atoms might change state, they might join with other elements, but there's still going to be 10 hydrogen atoms at the end of the reaction as well. Okay, elements can't just disappear into thin air, and we can't just create more of something we never had to begin with. So what balancing does is it takes a look at how many you have of each element and balances them on either side of the equal sign, or in chemistry, that one-way arrow. So for this one, I'm actually going to start right here. It looks like we make 2 chlorine atoms in the product side. So that means we had to start with 2 chlorine atoms on this side. I only have 1. There's a secret 1 right there. So in order to make 2, it's kind of like math where you put a big 2 in front. Okay, that essentially multiplies like math to tell you now there's 2 chlorines and 2 hydrogens. So the chlorines are now balanced. We have 2 and we have 2. The hydrogens are now balanced. We have 2 hydrogens, and here we have 2 hydrogens. Let's check our last element, which is magnesium. I'm seeing 1 on that side and 1 on that side. This equation is now completely balanced, and it obeys the law of conservation of mass. What you can do if it helps you is you can put coefficients of 1 in front of anything that didn't need a coefficient. For example, we might ask you to do that in a numerical response question. But again, just like math, those ones wouldn't necessarily need to be there. The next example that we have is adding hydrogen gas and oxygen gas to make liquid water, or H2O. How many oxygens do you see on each side of the arrow? I see 2 oxygens on this side, and remember the secret one, only 1 oxygen on that side. How am I going to change this so the oxygens balance? I'm going to put a 2 in front of the H2O. Now there's 2 oxygens, and 2 times 2, there's 4 hydrogens. I need to fix the hydrogens on the reactant side so that there's 4 of them. What coefficient would multiply by the 2 that's already there to make 4? This is now completely balanced. On either side of the arrow, I have 4 hydrogens and 2 oxygens. So here's what we've been doing when we balance these equations. We're writing the correct proportion of reactants and products because the law of conservation of mass is known to be true. Our goal is to have the same number of atoms on each side of the equation. So here's the example we just did. We had to double the H2O so that we could have 2 oxygens. That balanced with the 2 oxygens on this side. We also, however, by putting this 2 in front, have doubled the hydrogens. There were originally 2 hydrogens. They've now doubled to be 4 hydrogens. On the reactant side, we then needed to put a coefficient of 2 so that 2 times 2 would make 4 hydrogens balance. Here's some more that we can try. Oxygen plus methane is carbon dioxide and water. Oxygen, look on your periodic table, is it a polyatomic element? If you memorize those, it will definitely benefit you when writing these. Yes, oxygen is a polyatomic element. And on the periodic table, if we look, oxygen has this gray background in the box. The gray background, if you look on your periodic table, is telling you that it's a gas at room temperature. So that's why I've put O2 gas. Now methane is CH4 gas. I know that because we work with that in the lab. It's what's coming out of the lab stations, and it's also natural gas in our houses. Another page to bring your attention to on your periodic table booklet is page 5. On this page, there's a whole bunch of common compounds that have special names. Right down here near the bottom, you can see methane is CH4 gas. This is another page. 5 and 10 are really good pages to go to if you can't figure out how to name something. Now that makes carbon dioxide. This is the section that we actually skipped. This is a molecular compound. As soon as you see the prefix di, that's telling you that there's 2 oxygens. You don't need to know how to name this. If there's ones that have molecular compounds in them, remember we skipped that lesson for now. You're just going to copy it from the answer key and continue to balance. You don't need to know how to name it. And water, H2O. And when it says water, we're just going to assume there that it's liquid, but lots of times water will show up in a chemical equation as a gas. And actually this one does. This one we'll learn later is a combustion. This is when you light fire to methane, and the water actually is water vapor. All right, to balance this, I usually start wherever I see the biggest number. So I see that I have 4 hydrogens on the left. Remember, we're working left and right of this equal sign. I need to make 4 hydrogens on this side. What can I multiply by the 2 that's already there to make 4? Now, I've just changed more than just the hydrogen. I've also changed the oxygen. Now I have 2 oxygen, but I also have 2 oxygen over here. So this whole side has 4 oxygens all together. On the left side, I'm going to put a 2 so that 2 times 2 makes 4 oxygens on the reactant side. Now there's one element I haven't checked. Carbon. Does carbon balance? 1 and 1, yes. So you can put coefficients of 1 just to show that you're completely done the question. Nitrogen and hydrogen make ammonia. Nitrogen and hydrogen are both polyatomic elements. If you look on your periodic table, you have N2 and H2. And ammonia, we will have to find in our data booklets. Here on page 5, it's the first one listed. Ammonia is NH3 gas. A tip for when you're writing this is to leave a little bit of space in front of what you're writing because you might have to put numbers in front to balance it. All right, this one has a little bit of a trick. I'm still starting with the biggest number I see, which is 3, and I'm trying to balance these hydrogens. So I need to think what number would balance 2 and 3. It's similar thinking to writing a fraction with a common denominator. If I needed to do that, I'm looking for in math what we call the lowest common multiple of 2 and 3. We learned in math how to put that in our graphing calculator, but really what a lowest common multiple is if you skip count by 2 and 3, what's the first number they both have in common? 2, 4, 6, 8, 3, 6, 9. The first number I said was 6. That was the same. So I'm trying to make 6 hydrogens on either side. On the left side, 3 times 2 is 6. On this side, 2 times 3 is 6. So I now have 6 hydrogen on each side. The next spot I look is anything that also got changed, like this nitrogen also got changed when I put the 2 in front. Now there's 2 nitrogens on the product side, and there's actually already 2 on the reactant side. So this is now balanced. All right, they become a lot of work when you have to go from the words to the chemical equation and then balance them. Solid sodium metal. When it's written by itself, it's just going to be sodium solid. You only put a number there if it's in that little box on the periodic table, polyatomic elements. Sodium is not, so it's just Na solid. Chlorine gas, I know, is in that little box. It's Cl2. To produce, put your arrow where it says to produce. Solid sodium chloride. We have named this one several times. Sodium has a positive charge, chloride has a negative charge. They already balance. So it's NaCl, and they've said solid. That's table salt. We work with that one a lot. Okay, go to the biggest number first. I see the 2 with the chlorine. I'm going to make 2 chlorines over here. How do I do that? Put a 2 in front. That just changed it to 2 sodium, so I need to change this to 2 sodium. Put a 1 where you don't need a number if you wish. Next example, mercury 2 sulfide is decomposed into liquid mercury and solid sulfur. This is something that we will learn in the future. This just means it's a special chemical reaction called decomposition. That's just where your arrow is going to go. So mercury 2, when I see this 2 Roman numeral, I know that it has a charge of 2 plus. Looking now for sulfur on my periodic table, I see that sulfur has a charge of -2. So these 2's have already balanced. So I'm just going to write mercury sulfide without any numbers because they're balanced. And I don't know what state this is. They aren't telling me in the words whether this is solid or aqueous. So that's when I go to my solubility table. I'm looking on the top for mercury or sulfur. Looking, I don't see either. The only category it could fall in is perhaps group 1 ions, if mercury or sulfur were in group 1, but they're not there either. So what I want you to do is if it doesn't show up on the solubility table, you're going to default to solid. Okay, where it says is decomposed, that's where your arrow goes. Liquid mercury and solid sulfur. Remember, I got that 8 from that little box called polyatomic elements, and mercury was not in that box, so I didn't write any numbers at all. The biggest number I see is 8, so I'm going to start by creating 8 sulfurs on this side. Remember, there's a secret 1 there. Now, by creating 8 sulfurs, I also created 8 mercuries. I need to balance that there. 8 mercury, 8 mercury, 8 sulfur, 8 sulfur. This is now balanced. Methane gas reacts with oxygen gas to produce carbon dioxide and water vapor. We already did a question exactly like this. Part A was the skeletal equation, so it was already written with plus signs and the arrow in it. Part E is the word equation. So it's the same thing. It's just asking you the question in a different way. So you can try this one again, pause the video, and see if you get the same answer as the previous slide. Here's some equations that are a little more complex, and they've actually gone as far as to write out the ionic compounds for you. So when you're thinking about these questions, you can see why it's so important to write ionic compounds properly. If you don't write the ionic compound correctly, you won't have any chance of balancing the equation properly. So again, if you have not written all of your practice questions and did your corrections on the ones you got wrong, video chatted with me to make sure you know how to name ionic compounds, you need to do that before we get into this stuff. When you're writing equations, if your compound isn't right, there's no way you'll be able to balance it. Now, these ones are more complicated because they have things like SO4 and OH. These are our polyatomic ionic compounds on the periodic table. So this was lesson 6, I believe. What I want you to think of is not that something like SO4 is S's and O's. I want you to think of it as one thing. Okay, so when I'm looking at balancing the SO4s, I'm actually going to cover it up. I see one SO4 there, and I actually see 3 SO4s here. See how I'm looking at the entire SO4 as one entity? That's what you want to do. Don't look at the S and the O separately. So I need to make 3 SO4s on the reactant side. Now that's changed my hydrogens, but what I see is I've got H2O on the product side. That's going to be my last thing I'm going to look at. Let's do the aluminums now. There's 2 here and 1 here. So I'm going to write 2 to balance the aluminums. Now the trick with the water is that you can actually write water as HOH. This helps you see that there's 1 hydrogen and 1 hydroxide. So like we see hydroxide over here having 3, we can actually make 3 hydroxides over here. Then we can see if we've got a balance of hydrogens. So hydrogen, well, there's 6 over here, so that's not going to work. What do I have to take into account when I look at this hydroxide? I have to multiply by the number I put in front. This is why we do balancing in pencil, because a lot of times with these harder questions, you go back and forth and you actually end up erasing your numbers and trying the next one that you think will work. So if I put a 6, now I've got 6 hydroxides, which 2 times 3 is 6 hydroxides here, and I have 6 hydrogens, and over here 6 hydrogens. So this is a nice trick. Change your H2Os to HOHs if you have hydroxide, and it'll be easy to balance the H and the OH separately. Last one. I've got NO3, but in my mind, I'm just imagining this is one thing. Like this is one blue rectangle. And over here, I have 2 blue rectangles. Sorry, this was 3, and over here I have 2. What is the lowest common multiple between 3 and 2? 6. What do I multiply this 3 by to get 6? 2. Over here, 2 times 3 is 6. So now my little blue squares are balanced. I have 6 blue squares and 6 blue squares on either side. Now I can go to the other things that I changed. I changed my cobalts to be 2. So change 2 on this side. I changed my zincs to be 3. So put a 3 on this side. Balancing equations is a lot of back and forth and a lot of erasing. Make sure that you set up a video chat with me if you need any help at all. I know this can be quite tricky.